Hello, everyone. I'm happy to participate again at the AGI conference. My name is Arthur Franz, and I'm going to give a talk titled Experiments on the Generalization of Machine Learning today. So a little bit of about me. I have developed my own approach to AGI, so to speak, which is in line with the compression school of AGI. My contribution is about, on the one hand, the development of a theory that allows for a more efficient but still hopefully general compression, data compression. And using that theory, I have implemented a inductive programming system called William, which allows the testing of the theory and is able to solve a diverse set of various tasks, like playing tic-tac-toe, recognizing geometric shapes, simple ones, predicting and compressing simple sequences, and learning from test cases, writing code given test cases. And today I would like to present the extension of that system to machine learning problems. First, I will tell you about the theory, a short summary, and then we'll dive into the way how William works exemplified on various machine learning tasks. So the way the incremental compression theory works is that you have a binary string that can represent any type of data, and you want to find a function that maps that it constitutes a short description of that string and can generate that string. So the way the incremental compression theory works is that you are looking for a pair of functions which are a descriptive map f prime and a feature f that constitute together an autoencoder, as you're all probably familiar with. And so the f prime maps the string x to a residual r, which is required to be at least a little bit shorter than x, and f maps it back to x and reconstructs the data, so to speak. And the theory shows that if the feature f is selected to be the shortest one, making that possible, then we have certain nice properties. And we can speak about the length of functions in the sense that computable functions are Turing machines, and they can be mapped to integers, and though they can in turn be mapped to finite strings, and therefore we can speak about the lengths. So, and one of the properties, one of the many results that we have derived in that theory is that the shortest description of a string, the Kolmogorov complexity of that string, can be decomposed as a sum of the lengths of the shortest features plus some residual. So the way it works, you find that autoencoder, compress the string a little bit, and then find a new autoencoder, compress it more and more until you cannot compress it anymore. And you're left with some overhead as well, of which we'll speak at the end. So, and another property is that if the string is compressible by a constant, a fixed constant, then the shortest features are also bound by a constant that lays the foundation for the hope, let's say, that we can actually find those short features by exhaustive search or by some other search. The way William works is in the following way. We don't, of course, work with binary strings. We have all sorts of data types, integers, strings, and arrays, and lists, and so on. And those data types can live inside nodes, which are called value nodes, and they're connected by operator nodes. So the whole representation is a bipartite directed acyclic hypergraph. Hypergraph is because inside of the operator nodes there can be graphs again, but this is not important for this talk. So And so you have a set of primitive operators given on the right as an example. And from those, the system can construct various graphs. Let's exemplify how William works in the example of outlier detection. So suppose you have got a list given of chars where all are the char A, but in the middle there's somewhere the char B. So it's an outlier. So additionally, you have the number 1 given that he's allowed to use, and then he has a set of operators that he can apply. And these different data types, I have provided them with a fixed binary encoding. So I can any data type or any data can be mapped to a binary string, and the length of which can be computed. And in this case, it has the length of 251, the total length here. So the way it works is he tries to search through all graphs that can be built here, sorted by their description length. So he tries simple ones first, and then goes on to more complex ones. So, and I show here only those that actually lead to the solution, but he tries actually all combinations. So now he takes the 1, computes the list containing only the 0. Another operator computes the length, and then get item gets the 0th entry of X of the target, and just takes out the char A in a list. Another operator repeats the char A 26 times and gets a list of length 26, but containing only A's, which is the clean version, the denoised version, essentially, of the data. And I will tell about the color coding in a moment. And finally, he uses set item by inverting it. So the target is given, the output is given, 1 input is also given, and he computes the other 2 inputs of the set item operator. So he essentially inserts the char B at the index 18 into the list of A's and gets what he should get. And as you see on the right, the color codes corresponds to the autoencoder I've introduced earlier. So the green part is the descriptive map, goes from top down, computes the residual, which is the list of blue nodes below, and the feature reconstructs the target again. So the way it works is that this is a cyclic graph here, and he searches for the bottleneck. So he searches for a list of nodes that separate the graph, and the sum of description lengths of whom are the shortest. So he searches for the narrowest part in the graph. And then finally you can remove the descriptive map, and you get a description of the noisy list. And as you can see, the clean list is also present here as a list of only A's. And you have achieved a compression rate of 82%, since the residual here is much shorter than the target. And this is just one step of incremental compression. In this case, he's already done. But in other cases, as we will see, he can take the residual cross-section, as it's called, as this list of nodes is a cross-section, and he continues to compress them further. So let's look at regression, for example. Now, in this example, there are 2 arrays, the X array and Y array. Y is given by 2x plus 18 plus epsilon. Essentially, X is given uniformly distributed between -10 and +10, and epsilon is an independent error term. And what he has here is simply a data set. So he doesn't know anything about dependent or independent variables. He just tries to compress it. So one thing he does is to apply the add operator and decompose y into 1 plus a rest. Essentially, he subtracts ones from y. And the reason, and this is already compressing a little bit, because smaller numbers take less bits, they take fewer bits to describe. So because the description length of a number n increases logarithmically with n. So smaller numbers just take fewer bits. And then he replaces the 1 by a2, and then by a4. And you see here the estimate, the red dashed line increases slowly, and then he replaces it by a 16, and then he uses the x. He subtracts x values from his residual. And what it means is now he has connected x and y in the graph. And that helps compressing, of course, because now he doesn't have to describe x and y separately. He can describe x and then compute y using this error that has remained here. And as the next step, he subtracts x again. And essentially, you have a noise plus 2x. X prime is a version of x. And noise plus 2x plus 17 is y. And as you see from the dashed line, he's already almost perfect. And as a last step, he replaces 17 by an 18 by adding again 1. And he gets that, and he gets a perfect fit. As you see, he has reconstructed the regression expression 2x plus 18 by incremental compression. Without knowing anything about regression, without specifying any objective functions, there are no least squares or something like that. The only target, the only objective function is actually the final description length of the data. So let's look at classification. Here I have to tell you something about the way discrete arrays are represented. For example, Boolean arrays, usually you would need 1 bit in order to encode true or false. So for every entry, you would need 1 bit. But if the number of true entries is much fewer than the number of false entries, you can represent a Boolean array as an index of a particular permutation of truths and falses. And if the number of truths is really lower than the falses, then you will get a much lower description length. Essentially, in the extreme case, if you have only 1 true value, you can just specify its index, and you get a logarithmic description length. That's the reason why it's advantageous. And what you have is here a data set of x values distributed like here, and the class here in another array of truths and falses is color coded here by the 2 colors. And you see already if x is smaller than 5, then one class should be selected. If it's larger than 5, then the other one. Let's see what William does with that task. William again subtracts 1 because centralizing data is just compressing, which is again one pre-processing step that often occurs in machine learning. And then he can subtract 2 again, and subtract 4, and you see the histogram is already more or less centralized. And in the final step, he subtracts 1. So essentially, that's this limit here, and computes a prediction of truths and falses. And then he applies a XOR operator to compute the prediction error by inverting this XOR operator. And essentially, the prediction error is only true where the actual class and the prediction differ. So in that sense, you can look at it as an error. And he selects that description because doing it in this way reduces the description length of the prediction error. If you have few errors, then it means you have few true values in the array. That means that this permutation index description is low, and then you have compressed. That's how it works. And finally, I would like to show you a decision tree example, which is quite similar. You have this classic example of three colors, setosa, three flowers, sorry, setosa, versicolor, and virginica. And their petal width is distributed like is shown in the histogram here. And you have again the target data consisting of an array of chars. S denotes setosa, C denotes versicolor, and V denotes virginica. C is not seen here in this shortcut representation. And the petal width is here the second array. And what he does here is, you see already here the solution. He subtracts one and gets a Boolean array. An insert is an operator that can be inverted to yield two arrays. This array is only contains those values on the left of the one, and the second array is all the values on the right. So, and again, since on the left there are only setosa elements, you have an array consisting only of the char S, and the permutation index description yields that this has a very low descriptor length, because it's very easy to describe an array consisting of the same element. And that's why he chooses to go in this path during compression. So as you see, by splitting the data as the at the threshold 1, he has compressed it and split it into two data sets, where in one data set there are only the setosa flowers, and in the other one the rest. And that's what the decision tree does, the decision tree classifier. And finally, he can continue then to split the versicolor and Virginia data further in the same way. As you see, no Gini coefficient is necessary here whatsoever. It's everywhere the same objective function for every one of these machine learning tasks. So, in conclusion, we have seen that machine learning can be seen as a special case of the general data compression, very much in line of the minimum description length principle, which is here exemplified by a general algorithm that can solve simple versions of all those machine learning tasks. And the same algorithm can also predict simple sequences, as I have mentioned, recognize geometric shapes, write code based on test cases, and play tic-tac-toe. So that's what we have achieved. And of course, you will have in mind what are the limitations. Can this be scaled up? And the answer is I don't know, but whether it can be scaled up, I hope so, of course. But currently, the limitations are the following. One is the accumulation of description overhead. So one problem you have is, for example, one line can be described by two endpoints, right? Which would be optimal. But you can also describe it by many sections of lines, or by many lines that are just attached to each other. So you have many endpoints. This is also compressing, but not optimally. And you have these, and this overhead is unfortunately also present in the theory, which is this O of S times log of L of X. And it increases linearly with the number of compression steps S. And I have to find a way to combat that. I think I do have already a good idea to do that, and it works more or less, but it's still there's still some work to do. And another drawback is that there is no search for alternative descriptions. So what the theory allows it, or what the theory guarantees, that is, you find some short description, but it does not guarantee that you find all short descriptions, or even not even two short descriptions. And the question is how to deal with that problem. So there's a lack of theory here that we have to deal with. And sometimes during when you want to describe the world, you want to switch perspective, so to speak. And so you have to solve that. And another thing is that even though the shortest features are for practical problems bounded by a constant, which is not a large constant, but still it is quite cumbersome to search for autoencoders exhaustively, as I have told. And another limitation is the lack of memory. So it would be good if he has found some descriptions, some subgraphs that are useful, and that he reuses them. And this is currently also work in progress. And I hope I can present something next time. So in conclusion, we have made progress in this compression school based top-down approach to AGI, where the roots go back to Solomonov induction and AIXI and the theory of universal intelligence. We've continued that work with the theory of incremental compression and made practical progress that I have presented here. So, having said that, I would like to conclude with Marvin Minsky's words in his final public appearance in 2014. Everybody should learn all about algorithmic information theory and spend the rest of their lives working on it, which he said half jokingly. And well, I've taken it seriously. All right, thank you for your attention.